Thank you for joining Groundwork Solutions webinar series today. Our topic today is our injectable barrier solution. This is Bob Moody. I'm president of Groundworks based out of Lakeland, Florida. And so we're going to be talking about our applications for installing injectable barriers using polyurethane for contaminant and groundwater control. So getting started here, a few administrative notes. During the presentation, all microphones will be muted except for the presenters. If you have questions, please use the questions area on the right side of your screen and put your question in. And what we'll do is at the end of the presentation, just to maintain the flow, we will go over the Q&A session at that point in time. So also feel free to use the chat option. One PDH credit will be available for participation in today's webinar, but I will caution that some states don't allow its use, so please be sure to make sure your state will accept our certificate. I can tell you that Florida will not, so I apologize for that. We're working on that and hopefully can do that in the future, but not for today. So in order to get the PDH, if you do require it, you will get a follow-up email about the presentation in which you can provide some feedback, and also if you require the PDH credit, you can select so on that inquiry and send it back to us. So today, just as the presenter, just a short bio on myself. I have been an environmental career professional, spent many years in the civil, environmental, transportation, construction industries. I've worked for environmental services business unit with waste management for about 8 years, about 25 years with a Westinghouse environmental business unit, and I've been with Eurotech/Groundwork Solutions for the past 5 years. So I've worked on some really neat projects in my career. Probably the first one was back in the late 70s, excuse me, the nation's first Superfund site, the Love Canal site up in Niagara Falls, New York. And more recently, I worked on the Deepwater Horizon spill incident in the Gulf of Mexico. So some interesting experience there. And I am past chairman and current board member serving on Florida's Construction Industry Licensing Board, which is the board that licenses all contractors in the state of Florida. And one other note, I'm a former DOT, Florida DOT car contract manager, and got a lot of experience, and actually our insights into offering this injectable barrier solution came from my time as a car contract manager, and I should explain what CAR means. It is Contamination Assessment and Remediation Services contract, and basically it's to support DOT whenever they encounter contamination when working within their rights of way. So a nice surprise today, we've got a guest presenter, Tim Harmon. Tim is a registered professional engineer. He's principal engineer at Handex Consulting and Remediation. 23 years of extensive experience in remedial things such as investigation, design, construction, implementation, project, and program management. And I know he's also spent some time working for AECOM as well as URS in his career. And Tim is also a former DOT car contract manager, and that's kind of how we come together for this the work that we've done in the past together, and also this presentation. And then the one other person involved in this presentation is Robert Armstead. He will be the moderator for our question and answer session, which will come at the end of the presentation. So our agenda, it's a pretty big one, and we've got a lot of people registered. We've got about 225 people registered, so great participation today. But it is a big agenda. I've got about 40 slides for PowerPoint. Tim's going to go over the independent case study. We'll have the question and answer period, and we're hoping to keep it to an hour, but we're probably going to be pushing the limit on that. So if you feel the need to jump off for lunch appointments or any other business necessity, please, no problem jumping off if need be. So with the big agenda, I will probably go over some of these slides very quickly. I think that the meat of the subject really is the case study that Tim's going to go over. So I'd like to spend a good deal of time, leave a good deal of time for him to go over that, as well as question and answer period afterwards. So if I breeze through something here, we will provide copies of the presentation by email if you do the feedback at the end. And if there's a topic that interests you, please don't hesitate to contact any one of us. So Groundwork Solutions, basically we specialize in providing cost-effective, non-intrusive solutions for all things subsurface. About us, we're formerly, and many of you know us as Eurotech Holdings, Inc. We did change our name to more accurately reflect what we do. We've diversified our service offerings, so that's the reason for the name change. It's still the same people, same company. We're an innovator and industry leader in geotechnical polymer applications and trenchless sewer rehabilitation work, having been involved in this work for more than 25 years. So we're a Florida corporation, national footprint. We're actually operating in 31 states, and we're a licensed contractor wherever applicable. And we can provide necessary insurance and bonding. Now, we do have a very well-experienced, rounded management team. In fact, most of us came from that Westinghouse business unit, so we worked together for a good deal of time. And we've got a great safety culture, a 0.76 EMR rating, which actually I believe that we've surpassed 250 weeks now without a lost time accident, knock on wood. So the services we offer: structural foundation stabilization, sanitary and storm sewer rehabilitation, soil stabilization and densification. In our technologies, basically our Eurotech structural polymer applications, which is the foundation leveling and lifting. And so these are really our traditional stuff. And I think most of you guys know what we did in the past. So some of the new diverse offerings that we do are the APM Permaform, which is a cementitious lining system for sanitary and storm sewer systems. The Permacast cementitious lining, which is for pipes and manholes, vertical pipes and manholes. And then we offer Inversa, which is a CAT scan system to see through pipes to detect the void spaces and soil support stability. So APM Permaform, this is just a nice shot. It shows what we actually do, which is to centrifugally cast a plasticized structural concrete lining inside of a pipe, and it's a renewal system that's very, very cost-effective and quick. Can cover ground very quickly. And I'm actually going to spin through these slides here pretty quickly so that we can get to the meat of the presentation. So basically, there's two applications for the Permaform. One is a vertical spinner head, which is on the top right. The other one is a horizontal spinner head, which is on the left, on the bottom right. And as you can see there, you can do various designations or configurations of pipes to do renewal methods. And this is just a project we did, and it's kind of interesting to see the difference between the before and the after picture after it's been renewed. So Inversa Systems is an asset assessment tool that we use. It's a CAT scan system. It sees through pipe and can tell if there are voids and structural stability issues. And so that's kind of interesting because what we do after that is use that information to do renewal, both from inside and outside the pipe. And this is interesting. This shows the CAT scan image with the one on the left showing no void space, and what you're looking at the top is the outside of the pipe. And then you're seeing a transition to a void space, and then the void space for the picture on the right. Okay, so getting to this traditional service offering that Eurotech has done, basically we offer geotechnical polymer solutions for soil and subsurface issues. We do have a patent on increasing the load-bearing capacity of soils. So we use soil densification, void filling, structural lifting. It's a very highly controllable and structurally stable procedure. And the application's got 3 steps to it. One is surgical application via steel tubes. The second is a proprietary plural component expanding polymer. And the third part of it is that we monitor at the surface to detect any movement, which movement would indicate we've fully densified soils. And this is just a shot of some of the stuff that we do with the Eurotech polymers. This one, in case being sealing up a manhole and pipe and also stabilizing the soil for the road surface that's above it. And we do a lot of work in infiltration repairs as well. This is an interesting project in which there was substantial cost savings. We more recently did one in Florida here where a client had a 900 gallon per minute inflow into a wet well that was causing a 1.269 million gallon a day infiltration, which is very costly. They had a blown elastomeric seal in the manhole that was down about 26 feet below the surface elevation, and we were basically able to stop that leak within 15 minutes, about 95% of it within 15 minutes time. And then we had some fill-in detail to do, and within 2.5 hours we got that thing fixed for them. So that application, they went from 160 run hours per week on their pump system, which was a duplex pump system, to approximately 12 hours per week. So that was a big savings for them. And then there's another one here where we lifted a 4-barrel box culvert. It had been undermined by erosion. It was down 25 inches, and we were able to put it right back up in its original position. So getting out of the meat of the presentation here, our injectable barrier solutions. Couple things, definitions, and one thing I should add here right up front is that we are very pleased that we just received a service mark on this process from the U.S. Patent and Trademark Office. So what that does is that it identifies a service that a company offers that differs it from something that someone else may provide. So we're very pleased to actually get that service mark in place. So some definitions for injectable barrier. Injectable basically is the act of forcing a liquid into something. Barrier being something that blocks or prevents movement. And so the injectable barrier is injection of a substance into the earth, which forms a means of restricting the movement of water and or groundwater from one area to another. So there's a couple of different service offerings that we have that really fit this discipline. One of them is for environmental containment and control, and that's really the topic we're going to talk about today. And it is for construction support, which would be for let's just say when and I'll use an example. A DOT contractor is working through an area. Everyone knows there's a service station on just about every big street corner. Inevitably, when a contractor is working that area, the tank has leaked at some point in time from the service station, so there's contamination in the soil and groundwater. And what happens is as soon as a contractor starts to dewater to do an installation of, let's just say, a storm drain, a sanitary sewer, or some other utility conveyance, they start to drag the contamination off parcel and into their excavation, and we all know the problems that causes. So what we do is provide construction support by installing an injectable barrier that can keep the contamination plume from moving from one area to the other. The other environmental containment and control service we offer is environmental remediation, and that would apply to, and we're not going to talk about this today, but it would apply to something like using it for a soil gas vapor extraction system in which you're trying to pull contaminated vapors off out of the soil, and the injectable barrier can be manipulated to be installed to control the draft that's pulled on a situation like that. And Tim may mention during his case study a little bit of impact we had on an adjacent site while we were doing our injectable barrier on Okeechobee Boulevard in Florida. So the other thing that we offer this service for is for seepage management for dams, dikes, levees, and water control structures. We all hear about weakened levees and dams and what have you, and we do a fair amount of work in installing this product to stabilize structurally and to restrict groundwater movement from the contained area to the non-contained area. So some variations in the injectable barrier. There are two. One is a temporary, and the other is a permanent. The temporary would be for something like construction support or for environmental remediation, where you're just looking for a short-term solution. Construction support obviously is to maintain control while you're doing a construction effort. Remediation would be something like that soil gas system that I mentioned earlier, where it runs for a certain period of time and then you're cleaned up and you shut down. And then there's the permanent injectable barriers, where you're using it for permanent water cutoff and sealing, and that would be for dams, dikes, levees, and what have you. And then it would be also suitable for environmental containment, where you've got a plume of contamination, where you probably have got a vertical barrier to keep the downward movement to a minimum, but you want to control it from a a horizontal standpoint. So that would be a permanent application. Now, how it works? What we do is we inject polymer on a predetermined grid pattern. The polymer reaction, when it's injected, is immediate and absolute. The product is blended actually right at the injection site. So a unit comes to the site. They're fully contained units. They're driven. They're pulled with a basically a heavy-duty pickup truck, about a 28-foot trailer, self-contained. It's got everything necessary to do the installation. So it's outfitted with compressors, generators, dryers, tankage, a proportioner that brings the product to the correct temperature. It pressurizes it to get it to the gun, and also forms a perfect ratio, 1-to-1 ratio of the ISO to the resin. So this is a twin component material. What it does is it's blended right at the injection site. The product is propelled through the soil once the reaction starts by CO2 gas. CO2 gas is a product of the reaction. And what it does is then the resin's propelled by the CO2 gas. And it actually attaches to those gas bubbles. It fills the void space at the injection site by displacing air above when you're above the groundwater table, and it displaces water when you're below the groundwater table to basically to fill the space. So it forms a rigid, greater than 90% closed cell structure, cures within 15 minutes. And what you do is in your grid pattern, the subsequent injections bond to each other to form the barrier and also compact soil in between injections. And the barrier doesn't have to be, in a temporary situation, doesn't have to provide absolute coverage. A lot of times it will restrict movement even when it doesn't have complete coverage, simply from compaction of the soils. You're densifying soils between one injection site and another one, so you don't have to have that complete coverage. So some design considerations typically, let's say on average we're on basically a 3-foot by 3-foot spacing between injection points, so that's 3-foot vertical, 3-foot horizontal. Typically your shallowest injection will intersect the groundwater elevation, with your deepest being 2 or more intervals below any dewatering points that are in place to support construction efforts. As you go from surface down, each quantity is bumped up by about 5 pounds per interval. And for most of the work that we do for temporary injectable barriers, we do single rows of injection points, but also if the design life's a little bit longer, if you're doing a permanent barrier, definitely consider 2 or more rows of injection points, and those multiple rows should be offset. So obviously, you've got to place them all in an intercept position from the contamination to where the construction is taking place. And typically, URTech, we provide a number of different formulations of the polymer products, but what we would use for the injectable barriers is the 486 star 4-pound regular, which is a 4-pound density per cubic foot. And it's got a very, very good propensity for working within the water table. So the reaction's not impacted by water, and the cure is not impacted by water. And the 90+ % closed cell structure actually forces the water away from the reaction site, so it's not impacted. So this is kind of just a 3D rendering of what takes place underground. You like to believe that you get a nice, perfect 3-foot sphere of material that is placed in the ground, but considering soil conditions being so variable, typically this material will follow the path of least resistance. So the nice thing is it goes where it's needed. So you don't have a perfect sphere of material. It's a little bit modeled for this example, but it still gets the job done. So when you're looking at a project, you do want to look at, there's a lot of information to gather. Specifically construction plans and specs. You want to look at the plan view, you want to look at the profile, you want to look at the specification to see what's being done, what's the reason for doing the construction work, Then you want to take a look at the contamination data, which can come from your CAR report, your phase 1 and 2 environmental assessments, or in Florida, they do impact construction assessments, which have very valuable information with respect to contaminant concentrations, the various components, groundwater flow direction, and what have you. So also you want to take a look at geotechnical data. This is a very important piece of information for us. The soil boring logs give us everything really that we need to know about the soil so we can design a pretty good plan for moving forward. So the site lithology is important, groundwater elevation is important, flow direction definitely is a big one, and transmissivity data helps us to figure out how much material to put in the ground to make sure that we don't have any pass-through issues. So some other things to talk to when you're getting involved in a project like this, and Tim may mention this, but there's a lot of stakeholders. You've got the construction contractor typically, you've got a CEI, you've got a contamination contractor, you'll have the various regulatory agencies, you'll have the municipal utility departments, so there's a lot of players, and it's good to pull everybody together and figure out exactly what's going on. And what you do is you talk about the type, depth, and duration of construction. You talk about the dewatering effort that's needed to support it, and one biggie is to determine right up front any potential utility conflicts. Those utility conflicts, if there's something lying in the way of the injectable barrier, you want to make sure you account for it, and to figure that out up front is a big bonus because it basically can impact your injection plan. Now the nice thing is that this is a soft installation technique. There's no excavation. Basically, you're drilling a hole in the ground. You're inserting a 1/2 inch diameter steel tube to get down to the target depth. So if you do have utilities, you can pretty much work around them by hydrolancing, and so you don't drive your tubing into, let's just say, for example, a VCP sewer line that comes through the area. And you can move your injection points around a little bit. For example, if you can't get to an exact interval spacing, you can move that just slightly. And what you do is you can increase on one side and decrease the injected quantity on the other side and still get the same uniform spread. So in installation, utility locates, again, meet the locator if possible, figure out exactly where everything's going. And I already mentioned increasing or decreasing quantities if the points have to be adjusted. Another biggie is maintenance of traffic. That's always an issue because in a perfect world, you can get out there, you can work in traffic, you can set up your maintenance of traffic, and things go exactly according to plan. But if you're working in a populated area, you've always got to worry about how long they'll let you keep a lane closed and issues like that. There's a lot of political pressures with respect to that stuff in populated areas. You want to make sure you have good safety protection, your vests, especially if you're working at night, and definitely working in the direction-facing traffic. So placement of tubes, the photo on the right there shows a typical cluster, which is 3 to 5 rods per hole. In this particular circumstance, there's 3 in one hole, 2 in the other. And basically, those go down. And this site specifically, we were injecting at 8 feet, 11 feet, 14, 17, and 20 feet. So what that does is covers that roughly 8-foot to 20-foot vertical profile with those 5 tubes based on the 3-foot center. We do hydro-lance to weed around shallow utilities, but also we do it all to jumpstart deeper injections. What it does is if we hydro-lance, we can throw a level on to make sure that the tube is plumb as we're putting it in place, and then we get around some of the deflection that can occur when you get down to deeper depths of, say, 20 feet or so. Definitely want to collect drilling debris immediately if you're working like in the roadway, which most often we are, because that stuff does get into the storm drain. It will cause issues. So you should consider protection of the storm drain system. And definitely we use aerial lift devices while we're installing these. No ladders when we're getting up to depth, getting up to the 20-foot heights for safety considerations. So while you're doing the installation, there's a lot of monitoring to make sure you don't have any problems. When we're installing this material, even though we're using it for an injectable barrier, it can travel and it can affect ancillary structures. So we want to make sure that we don't move anything like a sidewalk, a curb, the pavement. So we do have anything from, we always have a laser set up with target receivers over anything that might be impacted, so we can detect the moment of movement if it should occur, and then we stop that location. The other thing to consider is if you've got storm drains and sewer lines, if there's any question with respect to whether they've got leakage or what have you, like I mentioned earlier, the material follows the path of least resistance, which is a blessing as well as a curse, because if you do have a hole in a storm drain line, the product can't find it and fill it up. So that is something to monitor for, to make sure it's not a big problem. And then there's other monitoring during installation work, and that would be a car contractor, like the service that Tim Harmon provides, the CEIs, the clients, and they're looking at the environmental parameters. So with that, there was a case summary that Tim Harmon presented a few times, but I believe initially at the Florida Remediation Conference in Orlando in October 2013. So with that, I'm going to pull up that presentation. And Tim, I'm going to turn it over to you. Thank you so much for joining us today. Appreciate your participation, and I'll let you go have at it.
Thank you, Bob. I think you set up my presentation very well. This is a presentation that we had given previously, and it's about 36 slides, so I'll try and take you through it as quickly as we can. A lot of it's going to be review and touching on the concepts that Bob had brought up, and it's 3 case studies of implementations, and they happened subsequent to each other, and the first 2 in very quick succession. So we gathered a little bit more data and intelligence, and came up, we're a little bit more confident in the proof of concept, and we were able to employ some more monitoring equipment too. So we're, you can probably see the level of sophistication as we progress through the slides. But go ahead and advance to the next slide, Bob. Oh, there we go. So this is an interesting story because we, as Bob said, it was very much a collaborative effort. We had both everyone involved in this project had observed this type of implementation in some form or fashion, just not in this particular, or as a problem, as a solution to this particular problem. But I had first seen it, this injectable type material in order to seal off a trench. The picture that you're seeing in front of you over to the left is a schematic of the injection process. That middle picture, you see 2 guys actually in a trench. They had sheet piling on either side, and they're injecting it at the end of that sheet pile cut in order to seal off that part. And what that was, it was a project. It was the end of 595 going into Port Everglades. And there were 35 utilities that were going through a very narrow patch of ground, and there were some contamination aspects of that project. I was the car contract manager, and we had the responsibility for dealing with the contamination issues and even some of the installation during this process, but also working with the utility companies to make sure that they are able to smoothly get done what they needed to get done. Unfortunately, FGT was the 35th utility that was putting in a high-pressure gas main, so they had to deal with all of the conflict. And here that they had to go down, I think, to a depth of about 20 feet, angle below some conflict piping, and then come up and then into that cut where you see the sheet piling on either side, that center picture. Then to work their transitions in order to go through that area. So they put the sheet piling in to segregate out the contamination, but the problem was that it had an artesian effect. So the groundwater was flowing alongside that pipe into that excavation and essentially filling it as fast as they could dewater it. So they weren't able, actually faster, so they weren't able to maintain any progress. So everyone stopped. They came up with a solution, tried to inject this injectable grout, and it did a good job of sealing that excavation. So in the back of my mind, next slide, Bob, we had a problem come up on a, oh yeah, we should be on slide 3.
Yeah, I'm working on it. It's not advancing.
All right.
Okay, I'll get you there.
Yeah. So slide 3 is just going to talk a little bit more through the what the actual product is. The important part is the NSF 61 certification that allows this type of material to be utilized around potable water, and that was an important consideration. But here's some verbiage from the cut sheet and the manufacturer's Bayer. Okay, on to the next slide. Here's some pictures of what the injectable grout looks like, both with and without matrix. The photo on the left is it's essentially polyurethane foam, and then when you inject it into the subsurface in a matrix like sand or peat or anything else that might be in the material, it mixes and combines with that and solidifies and forms a somewhat retardant barrier. So on the lower left-hand side, you see some of the sand and the foam mixed. In that center picture, you see also on that bottom left too. You also see the injection rod with some of the solidified, one part of the solidified material actually in the rod. Depending upon the clarity of your screen, it may be easy to see or not see. And then that picture in the center, you have a little disc, which is the product mixed with the matrix. It looks like it's heavy. It looks like a little sliver of concrete when you pick it up. It's actually a mix of the sand and foam, so it's actually quite light. And if you just allowed that material to just free flow, where it's not in sand, it's just in a void, it would look like that foam in that center picture up at the top of the picture. And then over to the right is just a close-up of the material and the matrix mixed. Okay, next slide. So this is the first project where we decided to implement this technology to solve a rather difficult problem. This was Riviera Beach site. It was a roadway improvement project. The issue is they were installing a 54-inch diameter gravity storm sewer line through the center of the street, and it happened to be adjacent to a groundwater contamination plume. And that was an issue for us, mainly as a car contractor, a DOT car contractor. We're allowed to, our role is to deal with contamination, but we have to be in the contamination. This was a particular aspect of this project, is that if the contamination is outside of the roadway corridor, then it's up to the roadway contractor to make sure that he doesn't exacerbate any existing contaminant plumes. But just the scope and scale and size of this problem, and the construction had already started, that we had to come up with some solutions very quickly, and that's where the collaborative process came in. So the District Contamination Impact Coordinator for the DOT called a meeting. We all sat, including Bob, myself, and the project administrator, and a few other people who were involved with the project, to kind of lay out the problem that we were facing and try and come up with a solution. And the project administrator had used this material on a similar project in the nearby vicinity, but for a different purpose. And again, I had seen this on a recent project on the Eller Drive, like we showed in the initial slides. So it was still fresh in my mind as being a potential tool to solve this particular problem. And it's located, it was about a mile stretch of highway. It's pretty close to the intercoastal there, and it was fairly sandy soil. Next slide. So this slide's a little bit busy, but you can kind of see what we were dealing with up in that upper left-hand corner, excuse me, is the contaminant plume and the contaminant boundaries. It was an old gas station. It's now a Walgreens, and you can see some of the analytical data there in the slide. It was mainly petroleum. And then you have a bunch of water lines, some of them really quite old. In that center of that graphic, you see the proposed underground drainage pipe. You also had some fiber optic lines that were coming close to that plume. Some of those water lines were very, very old and very brittle. So the water utilities was very concerned about anything that we were going to do in that area. So based on this lattice work of utilities, we had to come up with a solution that would both block that contaminant plume from going into the roadway and being drawn into that project corridor. And they were going to have to lay that pipe fairly deep too. It was going down, I think, about 10 feet. So that was going to be a substantial amount of dewatering for a substantial amount of time, and the cost to have to treat contamination that got pulled in with their dewatering fluids would have been very substantial. Next slide. Next slide.
Yeah, it's giving me a hard time.
I'm sorry, Bob. I know there's probably a delay here too.
Yeah, there is. Your next slide, it'll come up here in a second, but the next one is the solution, and it talks about the injection points, the intervals, the length, install time.
So when we bring up that next slide, it'll show the design of our injectable barrier. And keep in mind that we really haven't used this technology for this particular purpose. So this was all a learning curve for all of us. We had proposed that this might work, and we were willing to try it, and it seemed like the best solution based on the utility layout. It had the potential to be fast and clean and work around the utilities and be able to be installed quickly so as not to hold up the roadway contractor. And then you get into the issue of delays and delay claims and all of those type of things. So we were kind of taking, there it is. So we're kind of taking a risk, but you see what we came up with is the initial strategy and the design for this groundwater cutoff wall. It was going to be 58 injection points. I think Bob had mentioned the typical both horizontal and vertical spacing, about 3 feet. There you see the injection intervals. Went into some detail on the slide as far as how many pounds per elevation and how many pounds per point. This was a 200-foot wall kind of hooked there towards the end, just to make sure as they were working through that area and dewatering that it was going to be enough wall and enough coverage there. So the installation was 5 days. Keep in mind this was our first time doing this for this purpose. You see down on the very lower left-hand corner on that previous slide that you saw the injection pattern. So now we get into the monitoring. We developed a monitoring strategy just to make sure that this would work. And keep in mind, we threw this together it was very fast-paced and very quick from the time that we met to the time that we got together with Bob and Eurotech to kind of engineer this thing together and strategize together. It was a very quick succession. So we came up with the theory to install this as an engineering control. Again, the purpose to prevent the migration and the exacerbation of the groundwater contaminant plume. We did some hydraulic monitoring. We installed a data logger behind the wall to collect continuous water level monitoring during the dewatering period. And then as a fail-safe in the process of providing proof of concept, we had a dewatering treatment system on site and as standby as a secondary control. We ended up using it initially and just keeping it on just to make sure, and we collected influent and effluent samples twice daily for petroleum parameters. Next slide. So the next slide will take you through, we actually, the DOT won a Prudential Davis Productivity Award as a result of this implementation for the concept. We had, by being able to enact a very quick and elegant solution to a very difficult problem, we anticipated that we had $300,000 in cost savings to the taxpayers of Florida. The title of the award was Avoided a Groundwater Contamination Plume through Innovative Construction Methodology and Use of a New Technology. Although it wasn't a new technology, it was an innovative use of an existing technology for a new purpose. And next slide. And again, the benefits. Oh, yeah, the benefits. We actually through this application on this particular site, we proved that it's it's a functional technology. we did prevent the plume migration within impacting active utilities and businesses along US 1, which was very important. And even more importantly, that this was a major topic of discussion when coming up with this strategy. Another option was costly and time-consuming redesign. And at that point, they were just about to come through that area and were full into implementation, and to stop everything and redesign it would have been a substantial effort and resulted in a lot of standby time. In this case, there was a lot of community concern because we were choking a key access point during rush hour traffic, and so that was a very important concern. The longer the project drug on, the more upset the surrounding businesses and commuting public that they were kind of losing their patience with it. So a nice thing about this implementation, it worked so well that the roadway contractor actually gained about 2 to 4 months on his construction schedule. He was actually ahead of schedule after he came through this area. So that was an added benefit. Okay, the next, I'll take you through next slide, and then we'll take you through this case study. Happened right after the Riviera Beach. That this was in Okeechobee. Again, it was another roadway construction project that was going. This time, we were going by an active gas station with known contamination impacts, and that gas station was about to go into active remediation. Unfortunately, it was that didn't happen, but before the construction, so it was happening kind of concurrent with what we were doing, which at the end resulted in some interesting benefits associated with that. So next slide. So here's the setup on this second implementation. You see the active gas station there on the left side of the picture. There's a proposed drainage structure location, which is going there right at the edge of the intersection, that green box. Next slide. And here's a problem statement. We have, there's a contaminant plume that you see in red. We had, there was going to be dewatering, which was going to be required to install this drainage structure. We had a predicted dewatering radius of influence about 75 feet, which was going to start, which is definitely going to impact that contaminant plume based on the calculation. We had developed a dewatering influence calculator for the DOT to use in these type of circumstances as a tool. So we knew that we were going to have an issue once we performed that analysis. Next slide. So our plan was to do a cutoff wall, this time a different configuration. We were going to cut off that intersection L-shaped wall. This time we're getting a little bit more sophisticated and savvy. We're putting temporary monitor wells on either side of the wall to place data loggers to get a little bit more data. You can see the design of the dewatering well points around that green proposed drainage structure. Of course, the hydraulic gradient was right towards, would be naturally drawing that contaminant plume towards that drainage structure and into the road. In this case, putting that cutoff wall, now it's going to be pushing it into that cutoff wall. Next slide. So our plan here was to have physical controls, which was the groundwater cutoff wall, mechanical controls. We were still going to have a dewatering system on tap just in case there was any leakage to that wall. We'd be able to handle it. And then we would still needed to get a little bit more confidence in the proof of concept in a different situation, in a different environment, different setup. And then we had our management controls, which was the extensive planning that went into this, monitoring and sampling protocol, and then have someone on site observing, evaluating, and adjusting the system as necessary. Next slide. So we had some governing assumptions here. This kind of talks you through some of the specifics of the site. It's a fine sand. It's nice white beach sand. It's another area in West Palm Beach. It was close to the intercoastal. So that sand was present from 0 to 40 feet below ground surface. We got that from the geotechnical report. I think Bob had mentioned that earlier. Pulling all of your data ahead in advance of the design and implementation is key. Here the depth of water is about 9 feet. They're going to have to dewater to 15. The estimated aquifer thickness was 152, hydraulic conductivity about 3 feet per day. We had used an analytical model to evaluate the radius of influence and the dewatering impacts associated with that. Next slide. Continuing on with the governing assumptions, we're going to install this as a physical barrier between the contamination and the planned dewatering area, about 125 linear feet of cutoff wall this time. Injection interval was very similar to the last one, 8 feet to 20 feet below surface, using the same product, and has some admirable material properties, and it has an excellent chemical resistance. Next slide. A schematic of the dewatering system that was on the tail end, just in case anything came through that wall, we'd be able to treat it. Next slide. Yeah, and we get a little bit more into the collaboration here. I mean, this was really a bunch of people coming together to agree to the concept and allow it to move forward. And that was DOT District 4, Handex, Eurotech, Bergman Associates was the CEI, the project administrator. Ranger Construction was the roadway contractor. Johnson Davis was the drainage. Palm Beach County was integral in this too. They were obviously concerned about their utilities, but we also needed their buy-offs for the dewatering and handling of the contamination. Same with the South Florida Water Management District. URS Corporation was the one who was actually installing the remediation system on that corner gas station that we were installing the cutoff wall around, and then Palm Beach County Utilities. Next slide. So here's the graphic. Similar situation. We have a corner where we need to actually inject a cutoff wall, and we have a lattice work of utilities. Some of them would be quite expensive if we damaged or broke. Again, it's a similar concept where they have the underground drainage line, except this case the drainage line was actually existing. They were just installing a structure on top of it and continuing it on. There was a fiber optic line on this intersection too, an underground gas main, and a few others. So it was a pretty tricky implementation. We certainly couldn't have gone with the more conventional methodologies like driving sheet pile or something like that. There were just too many utilities to work around. Next slide. So here's a graphic which shows the injection points. We went with 41 points here, and this was a little bit different in that it was L-shaped, but it was also a little different too, in that we had so many pipes coming into that corner that we had to spread out our spacing where there were utility conflicts, and how we compensated for that is we just injected more material into those points to try and close that gap. So there's a little bit of variations. You see the variations there on the call-out box between the pounds per point. And toward that intersection where we had to bridge the gap, we used more pounds, and where we got to the end, we were able to get by with less. Next slide. So here's a transition, some pictures showing the implementation. Up there on the upper left-hand corner, you see them pushing the rods in for the injection process. On the upper right-hand corner, you see the rods in place, ready for injection. Down on the lower left, you see the technician there with his apparatus. There's two lines that go through that coil, and then bring those two components of the product down into the rod where they activate and set up. And then towards the end, on the bottom right-hand corner, you see the intersection after we're all done. So it goes in very quick, very smooth, very clean. We don't disrupt traffic. We don't, you can get in and out of there, and it's a very clean process as a result. Next slide. So we had a more intensive groundwater monitoring plan here. We had those two temporary monitor wells on either side of that wall where we were monitoring the data. We were doing manual measurements with the water level indicator just to have some backup data. And then we also installed a troll data logger in both of those monitoring points so that we were able to get some good data and some frequent data. And then we were doing contamination monitoring twice a day, in the morning and the afternoon, for petroleum constituents. And we also collected groundwater samples from TMW2, which was the one outside of the wall. Here you see the dewatering treatment system. in relation to the, you see both the dewatering system and also the dewatering treatment system. And these are some specifics about the flow rates. They started off at 78 GPM and steadied out at about 40. Next slide. Here's a graphic on us installing the Troll data loggers and the setup screen and the apparatus. It was good to be able to grab this data on this implementation. I wish we were able to be as extensive on the first one, but we were able to get additional data and a more sophisticated setup on this one, as mentioned previously. Next slide. So here's the data, which was pretty interesting, graphing the results that change from static. So that upper chart in the blue is TMW1, which is on the contamination side of that cutoff wall, and then you have TMW2 in the red there, which is on the dewatering side, on the other side of the wall, on the clean side. And the interesting thing about this, well, there's two interesting blips here on the graph, especially for TMW1. We saw dramatic change from static initially in the very, very early time data, where we probably had some leakage through a wall or a pipe or some other type thing, but it seemed to seal itself up, and then you have very little change from the initial static concentration as time went on. We had a very very heavy rain event, as you can see on the mounding portion of the blue there. You see it both in the blue and the red on both sides of that wall. Very intense rainstorm came through towards the tail end of the project. And then on that lower graphic, you see the drawdown on the other side of the wall down to about 3 feet, which was in line with what we had expected, and that stayed fairly consistent other than that mounding when the rain event came by. And that's going to be important on future slides. Next slide. Oh, here we go. So we did our analytical testing on the TMW2 and the influent and effluent of our dewatering treatment system, and those all came back clean throughout the duration of the dewatering event. Next slide. So here we have the law of unintended consequences kicking in, which in this case it was a good thing. But I got a call about 7 o'clock in the morning after they were able to start tapping into that stormwater line, and they found foam inside of it. So they thought that the injection process had actually filled up and clogged up their pipes with foam. It's a call you don't want to get at 7 a.m. after the implementation of a project like this. So we were trying to figure out what was going on. It turns out that where they were putting that or tying into that drainage structure was a low point, and that pipe was actually heavily cracked upstream where we had injected our polymer. You can kind of see on that upper right-hand picture, it's foam, as if what you injected was free-flowing into a void. That's what you would see. So going back in review of the literature, down there is an excerpt from that, is that this product also seals joints and cracks. You'll find outcropping of polymer, and then they usually come in and hydroblast the interior of that line in order to complete the sealing process and have the proper flow, smooth transition inside that pipe. In this case, nature did the hydroblasting. There were cracks in that pipe that no one knew anything about. The material sealed it, as well as sealing off the contamination. And then that big heavy rainstorm from Mother Nature did the hydroblasting for us and carried all that outcropped foam down to that low point where it was just by happenstance was very easy to collect and clear out of that pipe. So crisis averted, and we had some good consequences as a result. Next slide. So here's a timeline. There was a remediation system at that gas station which was being installed concurrently, and this is just a timeline where they were doing their system installation and we were doing our groundwater cutoff wall. So they essentially installed the remediation system, stopped, we installed our cutoff wall, and then after the dewatering was finished, then they started up the remediation contractor had started up their system, which was an air sparge SVE system, and this was more collaboration between the DOT and DEP, both coordinating around each other's efforts and also reinstalling some wells that were impacted by the project, by the roadway project. Next slide. So here's a setup of the remediation system. You can see the air sparge wells, which are the triangles, and the vapor extraction wells, which are the rectangles. And on the picture on the right is actually a photo where you can see the piping trenches and some initial vacuum readings, and also the sparge readings. The vacuum readings are in blue. The sparge readings are in green. Next slide. So I was trying to take the results and see how this, there was questions about how this cutoff wall was going to impact the remediation system. So I tried to parse the data as best I could, and I plotted pressure as in distance from the wall, and also vacuum in distance from the barrier wall. And the vacuum, if I was a little bit more sophisticated, I probably could have done that on a negative scale, but instead I made everything positive and just called it vacuum. But it still has the same trend, where if you go the previous slide, you can see the closer that you are to the wall, the higher or the more intense the vacuum, and also the more intense the pressure. So graphing the groundwater analytical data, I think I got a call from the remediation contractor upset with me because we actually significantly shortened their remediation effort. So they kind of cheated them out of some O&M budget. But as a result of them turning on that system and that groundwater cutoff wall being in place, there were some pretty significant drops in contamination within a very short period of time. So we were theorizing that that cutoff wall actually supplemented and assisted in the remediation effort, and the more contaminated aspects of that plume was able to impart more pressure and impart more vacuum as a result of sealing off that corner. Next slide. So the last case study, this is was probably the largest implementation of this type of strategy for a groundwater cutoff wall using this material in the state. And this happened afterwards, but this was injecting the material for a different purpose here. It was an arsenic plume on a roadway construction project where the AECOM was actually the car contractor, and they were trying to do some cleanup in advance of construction, and they were trying to shorten the time frame by installing this material as a cofferdam to prevent the clean water from coming in and diluting the arsenic and prolonging the pumping that would be required to treat and clean up that area. So it was pretty long. It was a lot of pounds, 32,400 pounds injected over 645 linear feet, essentially encasing the contamination within a cofferdam type of setup, and then they pumped out of that cofferdam through some activated alumina and re-injected the clean water back in. Next slide. It was fairly successful. I mean, the media that they used was activated alumina, and they treated the water, returned it, recaptured, and retreated to essentially a circulation system, but it kept the dilution down, coming from outside clean groundwater from coming in and diluting the arsenic. So they expected about 28 days at 250 GPM on that implementation. Next slide. So in conclusions, the injectable barrier, we found it to be effective in cutoff walls, and the implementations that we were involved with. It's had many benefits. It was cost effective. Keep in mind, sometimes on a roadway construction world, time is more valuable than money. So if you're able to speed up the schedule and fewer man hours associated with having to install a wall, like a traditional sheet piling, come back and vibrate it out with 2 implementations. Here you only have 1, and less man hours and less equipment that you have to do it. It's easy to install. It's a fairly permanent barrier. I think Bob had covered the 2 different scenarios. If it's only temporary, you kind of factor that in as far as how many pounds of material that you think you're going to need. But if you want it there a little bit longer, that needs to come into play too. And we found it to be fairly green too. You get a lower carbon footprint in terms of energy and emissions, and fewer equipment and man hours and personnel needed. And we've also found it to be an interesting remediation enhancement where we had higher sparge pressure readings nearest the barrier and also increased SVE influence near the barrier as well. The last slide. Here's my contact information if you have any questions following this webinar about these implementations that I've been involved with. And unfortunately, Vince is no longer with the DOT. There's been a couple DCICs who've taken over for him in the past couple of years. So his contact information is, you can contact the current DCIC, but they probably wouldn't have much information to give on these projects. But mine is certainly valid, and I encourage you to reach out to me if you have any questions or need some additional information as far as what went on behind the scenes as far as coming up with these strategies and coming up with a successful implementation. I appreciate the opportunity, Bob, to be able to present these case studies again.
Well, very good, Tim. Thank you so much. You bring a level of expertise to this that makes it all make sense, so really appreciate your time. We are, speaking of time, we are about out of time, so to be respectful and considerate of people's times, if there's anybody that does need to jump off, don't hesitate to do so. But what I'd like to do now is go into the question and answer session. There are a couple more slides that we'll pass over, but they will be available to be emailed if you go ahead and fill out the review, and so we'll make them available. So with that, Robert, would you go ahead and moderate the question and answer part of this?
Yes, I certainly will. So hello, everyone. Yeah, we've got some great questions, and so I would recommend staying through them. I think it's really going to help answer a lot of questions that perhaps weren't covered. So one of the first questions was, what is the procedure if there is no geotechnical or soil bearings available? Boring, excuse me.
Well, I'll take a stab at that, and I'll say that when you get involved in a situation like this and you are looking at installing an injectable barrier, you're talking about a fairly significant effort that really respects spending time and money on doing the advanced investigation work. It's imperative that we have geotechnical data. Is a minimum soil borings in a number of them, triangulation of groundwater flow, and the transmissivity data is very important as well. To not properly prepare for a project like this is probably a plan that has a considerable chance for not having success, and we'd hate to get involved in something like that. Tim, do you want to add anything more on that subject?
Yeah, no, I think you handled it very well. I mean, we were very fortunate on these particular projects because they were roadway reconstruction projects. We had a wealth of geotechnical data to tap into. I would say that's pretty important based on the level of effort and the cost for these type of things. The more information you have, the more you can. I think the better you prepare yourself for a successful implementation, or to be able to see issues before you go into implementation. The distribution of these materials, is kind of you can somewhat predict it, but there's some anomalies in the subsurface or slight changes in the transmissivity in the materials. You're going to want to know that and be able to account for that. So I would definitely say that getting some good soil data would be critical to successful implementation.
Okay,
totally agree, Tim. And the other thing is, I'll mention that there is a lot of information available in the public record. All states pretty much have an active listing, active database where they maintain records on leaking underground storage tanks, remedial efforts, and that can come from either the state level or the federal level as well, but also sometimes the county, the specific county has got a multitude of information that you can use to pull it together to fill in any gaps.
Okay, Can the material be injected into sheet pile interlocks with appropriate quality control to minimize leakage through this type of barrier wall?
Thanks, Robert. Yes, great question, and it has been used for exactly that. Sheet pile, sheet piling is an absolute method of hydraulic control, as well as providing a safe trench for workers. But then the issue with it is a lot of times sheet piles have got holes cut in them for lifting purposes, lifting and manipulation, but also the joints always cause some leakage. So we have in fact done injection around the joints specifically to stop the water from going through them. So the answer to that question is yes.
Okay, can the product be used to stop water intrusion into basements that are above the groundwater table?
Yes, it can. What it does is basically, that's a process that we call undersealing. So we can inject the material by drilling holes, as strange as that may sound, drilling a hole through a basement or a foundation, installing a compression fitting which our gun attaches to. The material is shot in, and what it does is when it hits the soil, it'll travel along the concrete foundation to soil interface, and it does what we call undersealing. So it can be used for that purpose.
Would this be applicable for installing a cutoff wall for SPCC containment purposes at a bulk tank farm near a water channel with silty gravel and cobbles and the first 5 to 7 feet below surface with clay material below 7 feet or so?
That's a great question. Yeah, yes, it could be used for that. For SPCC purposes, which I believe would fall under probably the EPA guidelines. What you would do there likely is a multiple, I'd mentioned multiple row applications. So it would, to provide an absolute barrier, you've got your vertical gradient covered by the clay layer. So what you would do is you would intersect on the horizontal standpoint the area that you wanted to protect. So it would be a multiple row offset pattern, probably fairly tightly spaced. And for design considerations, we'd need to look at all the hydrogeologic data that you'd have available, as well as the contaminant that you're protecting from, and any other permit conditions that were required of the SPCC.
Are the injection tubes removed after the material is injected, and does the poly adhere to the tubes?
Another great question. And yes, the poly does adhere to the tube, and there are certain circumstances where we do pull the tubes out, but generally they are sacrificial. They stay in place. One of the biggest reasons is by the time that you are able to disconnect the gun from the tube, from the injection tube itself, the grout has already cured. Now, from a chemical reaction standpoint, the process is immediate and absolute. Once you pull the trigger, the two materials combine, an exothermic reaction starts. So it's an organic chemical reaction, and what it does is it causes a mass output of CO2 gas, on which the resin it travels on. So when that gets in the ground, roughly 6 seconds after the trigger is pulled, the material starts its reaction, and probably within 3 minutes, it has pretty much cured. So it's awful hard. We get what we call grout lock. And so that tube is locked in place, and because of the depth and the cohesion from the soil above the injection site, as well as the adhesion effect of the poly to the soil at the injection site specifically, it's locked in place and we can't pull it out. So what we do there is basically we will try to cut the rod off at, let's just say we're going through a road surface, cut it off at the surface, and then we'll use a steel dowel, and we're able to drive that down below, so it's full burial depth below any pavement course. And then that hole is finished up with a twin component epoxy to seal up the borehole.
Okay. For this situation where the injectable barrier was used in conjunction with the sheet pile wall to support the construction project, was the sheet pile removed after the project? If so, were there issues removing it, or did it cause excess vibration when removed?
Yes and no. It was pulled out without any problem. So with sheet pile, there's some pretty big forces that are used to install them, obviously, and to pull them out as well. And there's a little bit extra required when you pull them out, but no problem pulling them out. Now, we also have done a number of projects where we've installed along concrete pile walls, like for seawalls and what have you, to seal. Obviously, those don't come out of the ground, but we've sealed up applications such as that.
For the last example, what happens to the area inside the cutoff box? Groundwater no longer flows naturally?
I would, yeah, I was involved on the periphery on that project just because AECOM was a car contractor. Handex had one car contract and AECOM had the other. So there were times where we worked jointly on projects, and that was a State Road 7 project where we had a couple areas and they had theirs. The nice thing about the product is that it's excavatable, so they were going to have to, there was a water line that ran right through there that was going to have to be taken out and rerouted, plus some of the drainage. They were actually installing ponds and associated structures with that. So they probably excavated some of that out, but what remains, yeah, it would still impede. It would still impede flow, what was left in place, I would imagine.
Great. So that kind of is a good lead into this next question, and it answers it somewhat. After injection of material, how easy is it to excavate through? So that was part answered, compared to controlled density fill. And how deep can you inject?
It would be very similar to excavating a DOT spec excavatable flowable fill material, such as a grout material that's typically used that doesn't require compaction for installation. So you wouldn't want to get in there with a shovel and try to do it by hand, but most certainly any power excavator will excavate it with ease. So that's not a problem at all.
Is the in-ground product any good as an exposed flowing water barrier?
Could you repeat that, Robert, please?
Sure. Sorry, give me 1 second. Is the in-ground product any good as an exposed flowing water barrier? I'm assuming that means when the material is exposed to the above ground.
Well, I'm not sure I fully understand the intent of that, and if the person that asked could kind of elaborate, that'd be appreciated. But I think I know the direction. The material is basically designed for geotechnical service, and that means for all prospective purposes, underground. It does not have UV inhibitors, so if it was used in a exposed position above ground, it would degrade over time. So we typically do not install this material above ground.
Yeah, I'd just like to follow on that. We had actually used this product to impede groundwater flow in our trenches for a roadway construction project. I think it was our Vero Beach project, where we actually injected on the sides of the excavation and below, because there had been so much rainfall in the area. And where we were working was actually between two water basins, natural watersheds and basins, and they were kind of overtopping into each other. And there was just nowhere to, even if we did dewater, we just had nowhere to send the water to locally. So we had injected on the outskirts of where we needed to dig to install drainage structures and drainage lines, and it did impede, as we excavated and it was unearthed, it did impede flow. That there were some areas where we actually cracked through it, and water came spilling in, but for the most part we were able to significantly limit the amount of contaminated water that we had to recover and manage as a result of pre-injecting this material into the area where we were going to be working.
Okay. I have a two-part question. For site number 2, did you have to close down the gas station while doing your work? And then the second part of that, will the leaked out gas flume eat through the Urotech material over time?
We didn't have to do any closures. Everything we did have to do some maintenance of traffic, so we had to. I think we may had to do a lane closure, but we worked with the gas station owner to make sure that we didn't impact his business. And in that particular case, we actually cleaned up, or the contamination cleaned up so quickly that in that particular case it really wasn't an issue. But another reason that we selected the material is that it does have excellent chemical resistance to the type of contaminants that we were dealing with. So we didn't expect any degradation of the material based on any chemical sensitivities or incompatibilities.
Okay. What do we find where do we find the in situ required information to know if a barrier can be successful?
I think that, yeah, Bob, you want to tackle that one?
I'd like to hear what you've got to say.
All right. Yeah, well, I thought you covered it so well in the introductory slides, but you know, there was a lot of discussion and collaboration with some people that had been around the block once or twice associated with this, which was nice. In order to come up with this concept, we had construction personnel and engineers and scientists and geologists and structural engineers and people who have a lot of experience in both sides of the coin, both on the DOT side and also the environmental side. So it's just putting all that information together. It's not really an easy analysis. It has to be done case by case and site specific by site specific, and having some good geotechnical data to work with too, and knowing some limitations as well of the material and the injection methodology. And it also all boils down to what you're trying to accomplish. You know, the end result. We kind of use these implementations for different purposes at different times to solve different problems. So I guess it all becomes, you know, it starts off with a problem statement, and then kind of going through that conceptually on what you're hoping the end product is, and seeing if it's a compatible solution with that. But definitely, you know, knowing the type of contaminants, if you're using it as a to prevent the exacerbation of an existing contaminant plume, knowing what type of contaminants you're dealing with, and knowing the hydraulics of the site, knowing the soil properties, and knowing any even imperceivable changes in the heterogeneity of the soil and what's in the subsurface, and knowing what the obstructions are. You know, sometimes you don't know. Sometimes you get in there and there's a bunch of buried debris that you have to deal with, or chunks of concrete, or very old utilities. And if it's old concrete pipe or you know, very brittle iron pipe, then there's, you know, chances are for additional leakage associated with that. So there's a lot of factors that go into that type of analysis. You know, it's something that we spent a few days on, and a lot of collective experience and expertise in order to reach the point that we did.
Okay, in the mountain states we deal with groundwater moving under roadways. Can this be used to create underground diversions that would help make underground water locations more predictable?
Well, that is certainly a possibility. Again, we'd have to look. Tim had mentioned gathering all the data available. So we would want to look at all the data that was out there, all the construction features, what utilities were in the area, what utilities cross or traverse the highway, as well as natural features, and take it all into account. But certainly we could use it for that purpose.
Is there a limit to injection depth? The examples in the briefing were petroleum sites, but what about solvent sites that have deeper plumes?
There is a limitation to the injection depth, and currently it's sitting right about 30 feet or so. We have injected deeper than that, but because of the reaction curve, the induction phase starts roughly 6 seconds after we start to combine the material. So you're limited in the travel distance down the tube to the injection site. So that's a challenge right now. Now we have done a we actually have done a DNAPL site barrier, and it was actually done in Fort Lauderdale on State Road 870, I believe. And what we had there was a former dry cleaner that operated across the road from a, I believe it was a utility complex structure that had to be installed. And so we put a barrier all the way around the area, and successfully were able to keep any contaminated groundwater from coming into and moving around the area.
Is the injected material compatible with petroleum products like gasoline, jet, and diesel?
Yes, absolutely. It has got very good chemical resistance properties to all those compounds, including benzene, toluene, ethylbenzene, xylene, methylbutyl ether, PAHs. The only thing that we've got some issues with, where there is some chemical attack, would be for substances like acetone and some concentrated acids like hydrochloric, sulfuric, and hydrofluorosilicic acids. But aside from that, there's excellent chemical resistance to any petroleum compound.
Can you use the curtain wall as a confinement device to maintain compaction or mitigate capillary action from stealing your backfill?
That's a doozy of a question. I mean, yeah, I believe you could. Obviously, it's a groundwater control technique, so if you were able to get a good sound fixed barrier around an area you want to protect, yes, that it could be done. It probably would not be cost effective to do it to the degree that would probably be necessary, but certainly if there's a specific situation, we would welcome the opportunity to take a look, evaluate it, and let you know if it is in fact a possibility.
Can this be used to create a barrier around the perimeter of a building with a sheet pile foundation over 20 feet below the groundwater table? Do the ports have to be placed through the sheet piling walls, or can they be done from above?
We almost always do our work from above, so yes, that could be done. There's occasions where we do work from the inside of a structure, specifically something like a box culvert, but typically most of our injections are from surface down.
Is there a table or a chart to predict grout take in various soil types and densities?
No, we do not have a chart. We do not have a chart that shows that actual relationship.
Do you have temporary barrier options?
Yes, I mean what we talked about today was pretty much a temporary barrier, which serves a specific limited duration service. So what we talked about today mostly was short-term, very limited, durational for a specific purpose type applications.
Okay, this is a two-part question. What is the in-ground life? Does it ever begin to decompose? And then the second part is, have you used this in an additional remediation tool in highway frost heave-prone areas?
What was the second part to that question, Robert?
Why don't we address the first, and then we'll go to the second. What is the in-ground life? Does it ever begin to decompose?
In-ground life is probably somewhere 60 to 70 years with absolutely zero degradation. There's been studies done by DuPont that show that the material can persist for much longer, in fact, 300 years or more. So we've had jobs where we've done installation work that has been in place for decades, and there's been no movement whatsoever. In fact, we did a job, I want to say, and I don't recall the exact duration, but I believe about 12 years ago, we did a job for a company that was a milk, it was a dairy operation, commercial operation. They had a large upright, I think it was a 40,000-gallon tank that was continuously, the level continuously varied in that tank. So depending on how much was in it, there was a certain amount of soil loading. And what happened over time, and we affectionately refer to the project as the Leaning Tower of Milk, because it did have a lean to it. And what we did was we were able to go in, and I believe it was about 12 years ago, we did injection work. We were able to realign the tank, densify the soils both directly underneath and in the foundational support area, and bring it back into perfect alignment. And just a few months ago, Golder and Associates went out and they remeasured that after being in place for roughly 12 years, and they found out that there's been zero settlement since the day it was installed. So, you know, that's more than a decade without any degradation or movement whatsoever. So I think that's a pretty good example of the material's longevity.
Great. And then the second part of the question was, have you used this as an additional remediation tool in highway frost heave prone areas?
Well, I think the heaving probably adds a degree of difficulty to what we do simply because of movement. But I don't know that we would definitely inject this material during the non-freeze cycle, and it really shouldn't have much of an impact at that point in time with respect to the installation work. I'm not sure I fully understand the question, so if the person asking it could kind of elaborate, it might help with a little bit better answer.
Okay, and then if you excavate through the material, does it leave a smooth surface or does it come out in uneven blocks? How deep can you drive your injection rods through a relatively sandy silt?
Okay, so we can get the rods down to 30 feet. Now that's a reach for us. Typically 20 feet is pretty easy. If we go down 30 feet, we probably want to get started with a hydro lance or a drill to get down to the target depth of 30 feet. And again, that's the limitation there is that it's hard to get the material to travel much further than that because it starts to cure. And what was the second part to that question, Robert?
Sure, sorry. How deep can you drive your, oh wait, that was the second part. The first part was, if you excavate through the materials, does it leave a smooth surface or does it come out in uneven blocks?
It completely depends on how much material is injected. For the purpose of an injectable barrier where you're limiting the groundwater flow, it would come out fairly smooth. If you've got a bucket that's got a sand plate on it, it's going to come out fairly smooth. If you're using it for densification and stabilization purposes, you're obviously injecting more material. So it's going to be more of a rigid monolith, and you might get some chunky effect out of it. But for the injectable barrier to be fairly smooth, you wouldn't cause a lot of damage to the surrounding unexcavated or undisturbed soil.
For deep injection, could you mix the resin and catalyst at the bottom of the injection rod?
Oh, I tell you, we're working on that. It's something that we've been trying to figure out how we can make that happen. A remote mixing device would lend itself to us getting down much deeper depth. So we're working on it, but nothing yet.
Is there a certain distance that needs to be kept from the barrier wall to maintain its integrity if an excavation is being completed in the area near the wall?
Well, yeah, you've got to look at the characteristics of the soil and the natural angle of repose. Traditionally, an excavation probably. The integrity of the wall is going to depend on what loading you have behind it. If there's no loading behind it, i.e. structures, vertical structures, then probably if you were to stick with the OSHA definitions for trench safety of the setbacks and your dig angles, we would probably be safe with that.
Can this be used as a barrier between water and sewer mains when the required horizontal separation between pipes cannot be achieved due to conflicts with other existing underground utilities?
Absolutely. This would form a permanent barrier between the two that, when injected with the proper quantities, would form a distinct cutoff that would not allow any migration of either the potable or the sanitary from one area to another.
Can this be used? Okay, that's great. Can this be used to improve riprap by using it to lock in place? Maybe if you don't have the required size to meet the design, a smaller rock might be used and locked in place. Maybe you don't have the required soil size to meet the design, a smaller rock might be used and locked in place.
Okay, so yes, it can and has been used for that purpose, specifically riprap applications on stream banks. It's been used for rail bed stabilization purposes as well. So yes, in fact, it can and has been used for exactly that purpose.
Does the material offer any thermal barrier? Say if I placed it to underseal a basement floor and installed along the basement wall.
Yes, absolutely it does, although the product that we offer is a geotechnical product. Everyone knows the spray foam industry was started because of insulation purposes, for insulation from the elements as well as for fire protection. And so the offshoot of that was the geotechnical applications. Now, we don't have any rating on our material, but obviously it does offer some degree of thermal resistance to it.
Okay. How does this compare / differ from permeation grouting?
Permeation grouting is a much different product. It's a single component material. It requires water and catalysts and promoters in order for it to do its thing. So it's a slow process as well. And from a cost standpoint, to accomplish basically the same thing, it's probably about 30 to perhaps 40% greater expense. The thing with the permeation grout is that when you inject it, you have to do calculations on the void ratio in the soil, and you actually have to displace any of the air or the water in order for the process to complete. And it's typically not used for a barrier simply because you have to space it very closely together. For example, if you were to try to do an injectable barrier with a permeation grout, you likely would have to do it on maybe 18-inch centers, and that may or may not actually get the column that you need to lock together. But it is a much slower process as well. For example, to do the profile between 8 feet and 20 feet vertically, when we do our injection work with the polyurethane, it takes us roughly 15 to 20 minutes perhaps to get that whole profile done, whereas with a permeation grout, it pumps at a much slower rate. And for example, somewhere between probably 6 and 9 minutes per gallon. And to cover that vertical profile, you probably have to have about 1.5 to 2 gallons per vertical foot. So you can do the calculation on that, but it takes about 4 times as long to do installation of permeation grout.
Okay, great. So that's it for the technical questions. There were some administrative questions, which I'll go on ahead and address real quick, Bob. So one question is, will we have access to the materials? Yes. We'll be sending in about 2 hours a follow-up email that'll take you to a feedback form on our website. Once you filled out that feedback form, you'll get access to a few different things. One is if you're looking for a PDH certificate for this presentation, that feedback form will indicate to us that you desire that. 2, it'll give you access to the presentation materials in PDF. And 3, it'll also give you access to our a video recording of this webinar, including all the questions here at the end. And fourth, it'll also provide an opportunity to register for a geotechnical aspects of polyurethane grout webinar with guest speaker Randy Post, who's a senior project engineer at Golder Associates. It's being hosted by our affiliate Eagle Lift out of the California, Nevada, and Arizona territories. So we'll give you an opportunity to register for that webinar there. And that's it for the administrative notes, Bob. And after a half hour, almost 40 minutes after the end of the webinar, we still have 75 attendees. So wonderful. But go ahead, Bob. Thank you.
Yeah, that's excellent. Great participation today. Great questions. Many thanks to everybody that devoted this last hour and a half to hearing about our injectable barrier technology. Thank you so much, Tim Harmon. Really appreciate you, your technical expertise. It's been great working together on the projects that we've done with DOT. And so, Tim, did you want to say anything in closing?
No, I think you covered it well. I appreciate the opportunity to participate, and I thought the questions were excellent. So appreciate the collaboration and the opportunity to participate.
Absolutely. Well, again, thanks everyone. You will get information with respect to the presentation today, so if there are any questions whatsoever, do not hesitate to call, email, contact us. Be happy to help out with any situation might be out there. Thanks again, and everybody have a great Friday and a great weekend. Bye-bye now.